Hello, so today we're going to find how to find the maximum, global maximum and minima of a closed and bounded region using a multivariable calculus. And so we're going to give you an example problem. This example problem I created on my own, but this is a modified version of a problem from the Serge Lang textbook. So let's start off by reading this problem. It says to find the maximum and minimum points of the equation 2x plus y squared with corners of positive negative 2 and positive negative 2. So the first thing to do this kind of problem is the 2x plus y squared is our interior, and the corners, which this will form a square, that's going to be our boundary. So let's draw the boundary first. That's the first step we like to take. And we have 2, positive 2, 2, negative 2, 2, 2, negative 2, and negative 2, negative 2. I could just draw this square here. Try to draw it as neat as possible. Okay, so this will be our boundary, and our interior is 2x plus y squared. So for the first thing that we have to do is we have to find to see whether or not there are any critical points in the interior. And so to do that, we have to first find the gradient of the interior. And so we do that. The gradient of this interior, so this is f of x of y, equals to 2, 2y. And we try to set the gradient equal to 0, 0, because as we've learned before, if the gradient of the equation, whatever you plug in that makes it equal to 0, 0, that will be a critical point of this function. But we can see here that even though if you plug in 0 here, you will get the answer 0, this 2 will always be a 2 no matter what you plug in. And so we can conclude at this point that the critical point doesn't exist in the interior. Okay, so we have that established. And so now that we know that the interior does not have any critical points, we're going to have to move on and stop searching here and try looking at the boundaries to see if there's any critical points there, which there should be. And it's easy because all the boundary points are linear, so you can kind of just use logic and reasoning to deduce where the critical point lies. And so let's redraw this graph again. Since we're using a new piece of paper. Alright, it's kind of messy. Okay, so we have these points. Let me label these so there's no miscommunication here. Right, so we got these corners of plus minus 2 plus minus 2. And as you can see, it's a square. And so how do we find the critical points for this? Well, right now we can't really find we already realized that there's no critical points in the interior. So what we can do here is, because this is linear, we can see which points will give us the maximum and minimum value, and that will determine our global maximum and minimum value, because we know that the interior does not have any critical points. So the global max or min has to be on the boundary. So the first thing is we could try different scenarios. So the first case number 1, we'll say that x equals to 2, and in this case y can be from negative 2 to 2. And so in this case, if you are, let's write the equation again so that we don't forget. F of x y equals 2x plus y squared. And so if we plug in our x equals 2 into that equation, that will give us 4 plus y squared. And we can see from this equation, within this range, y will always be positive. And so we can see here that the maximum value will be when y equals to negative 2 or 2. And the minimum value, well, you can see here that will probably be y equals to 0. Case number 2. This is a little messy here. Let's make x equals to negative 2. Y is the same. It will be from negative 2 to 2. as you can see here, x equals negative 2 goes from negative 2 to 2. Okay, and so again, if we plug it into this equation, this time we'll get negative 4 plus y squared, but it's still same goes. The max will be when y is negative 2 or 2, and min is when y equals to 0. Okay, so we established those cases. Let's move this upwards. Alright, what if another possibility is if y is 2, in which case x will stem from negative 2 to 2, as well. As you can see from here, y is 2, negative 2 to 2. Pretty simple. Alright, so if you plug it into the equation, if you plug in y equals to 2 into this equation, that will come out to 4, right? So it's 2x plus 4. And so looking at this equation, you can see that your minimum value will be when you plug in negative 2 into here. So because I'll give you a negative value here, and I'll give you the lowest answer, is when x equals negative 2. And therefore you can deduce that the maximum will be when x equals to 2, right? That'll give you the most positive answer, and so the overall answer will be greatest. And sorry, this is case 3. And so our final case here is if y equals to negative 2, and x as well will still go from negative 2 to 2. And if we plug it into our original equation, if we plug in negative 2 here, that will still give us positive 4. And so same answer as before, so we can see here that the minimum will be at x equals negative 2, max at x equals 2. So now that we have all our points, you see here that we have a total of 4 points, because some of these are overlapping, so we don't have to repeat. So let's draw out a chart of value. And so we could do negative 2, 2, 2, 2, negative 2, negative 2, 2, negative 2. And once again, our f of xy equation is 2x plus y squared. So now all we gotta do is plug it in. So if we plug in negative 2 and 2 here, that'll give us 0. If we plug in 2, 2, that'll give us 8. Plug in negative 2, that'll give us 0 again. And if we plug in 2, negative 2, that'll give us 8. And so we can see here that based on these values, the maximum value will be 8, and the minimum value will be 0. So the maximum value is at 8, and the points at which there gives the maximum value is positive 2, 2, and 2, negative 2, and the minimum value be 0, and the points that give that value is negative 2, 2, and negative 2, negative 2. And so we will say that these are the global min points, and these are the global max points. Okay, and that's basically how you solve a global max and min problem.